Hello and welcome. In this screencast, we will explore features of rational functions, namely x-intercepts, vertical asymptotes, and holes. Because any rational function is the ratio of two polynomial functions, it's natural to ask questions about rational functions that are similar to those we asked about polynomials. With polynomials, it's often helpful to know where the function's value is 0. In a rational function, r of x equals p of x divided by q of x, we're curious to know three things. What does the graph of r of x look like where only the numerator, p of x, equals 0? What does the graph of r of x look like where only the denominator, q of x, equals 0? And what does the graph of r of x look like where both the numerator, p of x, equals 0 and the denominator, q of x, equals 0? Connected to these questions, we want to understand both where a rational function's output value is 0 as well as where the function is undefined. To answer these questions, let's look at an example. Consider r of x equals x squared minus 4x minus 5 all over the polynomial x squared minus 5x minus 6. We'll start by finding the factors of the denominator. So we know x squared minus 5x minus 6 factors to x minus 6, x plus 1. So as a result, we know that x equals 6 and x equals negative 1 make the denominator equal 0. And since the denominator cannot be equal to 0, we can conclude that the domain of R is all real numbers except x equals 6 and x equals negative 1. And then we're going to move on to find the factors of the numerator. So x squared minus 4x minus 5 factors to x minus 5, x plus 1. Thus the numerator would equal 0 when x equals 5 or when x equals negative 1. So for this function, only the numerator equals 0 at x equals 5 from the factor x minus 5. Only the denominator equals 0 at x equals 6 because of the factor x minus 6. And then notice that the denominator and the numerator both equal 0 at x equals negative 1 because of the common factor x plus 1. So next we're going to look at the graph of r of x to see what happens graphically in these three situations: when only the numerator equals 0, when only the denominator equals 0, and when both the denominator and numerator equal 0. So in the graph at the left, we see that r of x has a 0 at x equals 5. So there's an x-intercept at 5, 0, and this was when only the numerator equaled 0 because of that factor x minus 5. We also see that there is a vertical asymptote at x equals 6, and that was where only the denominator equaled 0 because of the factor x minus 6. And on the graph to the right, we've actually zoomed in near x equals negative 1, and we've used our mouse to trace along the function until we land right on the point where x equals negative 1. And you notice the graph is not defined there. There is a hole. So the technology did not catch that on the graph on the left. You had to know to zoom in and look for that. So because the numerator and the denominator both had a factor of x plus 1, so the numerator and denominator both equaled 0 at x equals negative 1, there was a hole in the graph. So let's actually look more closely at the behavior of the function r of x near x equals negative 1. The hope is that we're going to be able to find out exactly where that hole is located. So here we see the graph of r of x zoomed in near x equals negative 1 again, as well as a table of values for r of x near x equals negative 1. So notice that as x approaches negative 1 from the left, the output values of r of x seem to be getting closer to 0.857 something as x approaches -1 from the left. And as x approaches -1 from the right, the output values of r of x seem to be getting closer to maybe 0.857 something again. So indeed, we see on the graph this missing whole is something just shy of 1. So the terminology we're using, where x is getting closer to -1 or from the left or the right, might remind you of limits. And so one thing we're noticing is that it appears that the limit of r of x as x approaches -1 is approximately 0.857. In fact, we can find the exact value of this limit and thus the exact location of this whole by using a simplified version of r of x. So specifically, we're going to look at the limit of x minus 5 over x minus 6 as x approaches -1. So what we did is we canceled out the x plus 1, the common factor. Now note, x minus 5 divided by x minus 6 is not equivalent to the original function r of x, because the simplified version would not have a whole at x equals -1 like r of x does. But by canceling out that common factor, we can actually evaluate this limit, because we can now let x equal -1, so we'd get -1 minus 5 over -1 minus 6, which equals 6/7. And using a computational device, 6/7 is approximately 0.85714, which is about the same value we saw in the tables as x approached -1. So what we can definitively say is that the limit of r of x as x approaches -1 is equal to exactly 6/7, which was approximately 0.85714. And so what that's really telling us is that the location of that whole is at -1 6/7. So remember, the goals of this screencast were to determine what does the graph of r of x look like when only the numerator equals 0, what does the graph look like when only the denominator equals 0, and what does the graph of r of x look like where both the numerator and the denominator equals 0. And we saw that if p of a equals 0, so if the numerator equals 0 and q of a does not equal 0, so the denominator does not equal 0, then r of x has an x-intercept at a comma 0. And we saw that if q of a equals 0, so if the denominator equals 0, and p of a does not equal 0, so the numerator does not equal 0, then r of x has a vertical asymptote at x equals a. And lastly, we saw that if p of a equals 0, so the numerator equals 0, and q of a equals 0, so the denominator also equals 0, right? And the limit of r of x as x approaches a equals a specific value, then r of x is undefined at x equals a. That's why there was that hole there. The function is undefined there. And as just mentioned, there is a hole. We'll word that better. And r of x has a hole at the point a comma